Hi, today we're going to look at how binary search and matrix multiplication work. We're going to utilize the divide and conquer methodology and implement these algorithms recursively. Starting with why divide and conquer is such a key concept in computer science. Firstly, it increases the efficiency of algorithms by breaking larger problems into smaller subproblems. Secondly, the concept leads to parallelism, where subproblems can be processed parallelly, thus taking advantage of multiple cores and reducing calculation time. The concept also leads to dynamic programming, where resources can be saved by storing solutions and avoiding redundant calculations. There are many uses of divide and conquer. Let's learn how it works using binary search and matrix multiplication. Let's first visualize the solution to binary search. Starting with the first requirement, we are given a sorted array of 7 elements. Now, binary search states that what we're going to do is we're going to split this array into half. We're going to calculate the middle. When we calculate the middle element or the middle index of the array, we compare this to our target. So essentially, let's imagine our target is 9. So in our binary search, we're given this array. In this array, we split this into half, and then we calculate the middle element. We check if the middle element is our target. If it's not, then we split the element into 2 halves. And how we search for our element is, even though we're splitting it into 2 halves, we're not searching in both the subarrays. Because this array is sorted, we're going to check if the target is larger than our key or if it's smaller than our key. Now, essentially, because 9 is smaller, we're only going to search in this subarray. So we calculate the middle. After we calculate the middle, 5, we check if 5 is equal to 9. If it's not, we split this subarray into half. Now, because the subarray has been split into half, we check if 5 is smaller than 9 or if 5 is greater than 9. Because 5 is greater, we only search in this, and that takes us three comparisons to prove that 9 is over here, or to find our target. And now you might be thinking, oh, but it would have taken us, doing a linear search over each element would also have taken us 3 searches. Now that is true if the target was 9. However, if our target was 52, it would have taken longer. However, no matter where the element is in our array, it would have taken us only 3 computations to find 52. Now let's go ahead and look at how this algorithm can be implemented in C++. Okay, so let's look at our implementation of the algorithm, starting with the main function. In the main function, I have defined an array of 10 elements. The array is sorted. Now, this is one of the most important requirements with binary search, that the array that's passed to the algorithm of binary search needs to be sorted. Now, I have an array that's already sorted. However, we can also implement a sorting algorithm and then pass it the sorted array. And we looked at in the last video. Then I have a target, which is 7. So we're going to look for the index where 7 is present. And then I have a variable n, which stores the size of the array. I calculate this by passing the entire size of the array and dividing it by size of one element in the array. Then I have this variable called result. The result is going to store the index at which our element is present. And then I have this, we're calling this function called binary search. And to binary search, we're passing the array itself, the size of the array, and the target that we need to find. And this goes over here into binary search. This is essentially a helper function for me and for every other coder. And I have this helper function so that when we are calling a function, we don't have to pass unnecessary things, the things that can be calculated by the code itself. So essentially at this point, we're calling our recursive function where binary search is recursively applied. We're passing our array, we're passing the low end of the array, and we're passing the high end of the array, and then we're passing our target. Now let's go ahead and see what happens recursively over here. Now the first thing that we do is we check if high is greater or if high is lesser than low. And if that is the case, we return -1. And we do this because either the target is not found or the array that's been passed is not sorted. And if any of those is the case, then we should just terminate it without having any further computations. Then we have int mid is equal to low plus high minus low divided by 2. We're calculating our mid element. Now essentially when we do low plus high by 2, that can lead to integer overflow because we're constantly changing our low and highs because we're going to be going through this function recursively. Then we have an if-else block with 3 else if blocks. The first if block checks if array of mid is the target, and if that is the case, we do that the target is found and we return whatever the index of our mid is. If that is not the case, we check if our middle element is greater than the target. If that is the case, we search in the left half of the array. And if that's also not the case, then we search in the right half of the array. And we're splitting this like we did in merge sort. Essentially, we pass the array itself, we pass a lower end, and we pass the middle end -1. And then for the right half, we're passing array and then middle +1. We're not looking at middle because we're calculating or checking if the target is in the middle element in our first if block. And that is how the binary search is recursively implemented using divide and conquer. We're dividing the given array into smaller subarrays and also only searching in the half or in the subarray where it can be found. And that's essentially because we have a sorted array that we can do this. If the array wasn't sorted, we could also search in both the subarrays, and that could also be one possibility. Let's go ahead and look at our second problem. Okay, so let's look at matrix multiplication using divide and conquer. So essentially, let's imagine we're given 2 matrices of 4 by 4. Now, essentially, what we're going to do with divide and conquer with matrix multiplication is we're going to divide the 4 by 4 matrix into multiple submatrices of size 2 by 2. Now, essentially, with these 2 by 2 matrices, let's imagine this whole matrix, which is a 4 by 4, as a 2 by 2 matrix. And now, essentially, we're going to fill these empty blocks, which is the resultant 4 by 4 matrix, in the manner that we would as 2 by 2 matrices. Essentially, starting with C11. C11 is going to get multiplied with A11 and B11, because in a 2 by 2 matrix, you would multiply this element with this element with this element, and then similarly, you're going to follow the same pattern, which happens over here. So C11 gets filled with the with the sum of A11 and B11 with A12 and B21, and then C12 gets filled with A11 with B12 and added with A12 with B21, B22, and then C21 gets filled with A21 with B11, and then A22 with B21, and then C22 gets filled with the addition of A21 with B12 and A22 with B22. And that's how we're going to fill these places. But essentially, we're dividing them up into a smaller subarray of smaller matrix of 2 by 2, and that's how we are dividing this and then conquering them through recursive multiplication. Now let's go ahead and see how we can implement this in C++. Now essentially this is a little more difficult in C++ than it is on Python, and that is because C++ does not have support for 3-dimensional or 2-dimensional matrices. We have to physically implement them as 2D arrays, and I do that over here with 2 vectors, where I have a vector with a vector that's decided with 4 elements, and these essentially are our subarrays or so. Now essentially let's go ahead and look how this happens. We have a function called matrix multiply recursive, which is over here. In this function we pass in our first matrix 4 by 4 size, and then our second matrix of 4 by 4 size, and then our third matrix, which we have initialized with zeros, of size 4 by 4, and then the size of the matrix, which is 4. Now essentially we're taking it would be 4 into 4, or it should have 2 different sizes, because the matrix can have two different lengths on the length and the breadth half. However, we're only taking 4 because we're only considering square matrices that can be divided into halves. Now essentially let's go ahead and see over here. Then we have a function called matrix multiply recursive auxiliary. In this over here we pass in let's go up and see the matrix multiply recursive auxiliary function. And over here we're passing our first matrix, our second matrix, our third matrix with the row and column of A, row and column of B, and then row and column of C, along with the size of the matrix. Essentially inside that, what we have is if n is equal to 1, that is if the matrix is of size 1, we perform we add to the C column plus C row of row A and column A, and row B and column B for B, and return. And this is when our recursive step has reached to the subarray size 1. But essentially we're going to divide the matrix by 2. We're going to call our function again, pass in new rows and columns for each of these subarrays. Now we looked at the picture. We're having to call our matrix multiply recursive auxiliary over each of these subarrays. So we have 1, 2, 3, 4, 5, 6, 7, 8. We have 8 subarrays for which we're calling the recursive auxiliary matrix multiply 8 times. And I have labeled them over here: the top left quadrant, the top right quadrant, the bottom left quadrant, and then the bottom right quadrant. Essentially, after we do that, we also have a function called matrix multiply add, and that just adds the matrix that just adds the matrices of the corresponding rows and columns. And that's how you solve matrix multiplication recursively. Essentially, this can be improved by something called Strassen's algorithm, because as of now, the divide and conquer does not bring any improvement to the matrix multiplication. Matrix multiplication without divide and conquer has a big O of n cube complexity, and with divide and conquer, matrix multiplication again has a big O of n cube time complexity. And that's it for today's video. I hope you enjoyed and learned something, and have a nice day.